series. And today we have a good one. The topic of today's webinar is particle image velocimetry, advancements in high-speed imaging. And I've been looking forward to this webinar for quite some time. Today we are going to be joined by a guest speaker. Dr. Kyle Gilroy from Vision Research Amitech is joining us. Hi, Kyle. Can you hear me?
I can hear you just fine. How you doing?
Great. Doing great. Thanks for being here. And I'm also joined by my colleague, Dr. Wing Lai from TSI. Wing, are you there as well?
Yes. Hello, everybody.
And yeah, so the topics that we're going to be talking about today, I guess I just want to briefly introduce our speakers before I get to that. And Kyle is joining us. He did his PhD at Temple University and also did a postdoc at Georgia Tech. And so we're excited to hear what he has to say. He has a lot of experience in the field of high-speed imaging and a lot of expertise there. So looking forward to that. My colleague Wing Lai got his PhD from the University of Minnesota and has many years at TSI working in the fluid dynamics group. So looking forward to what he can contribute from the PIV side. And a few bookkeeping things as we advance to the next slide here about the webinar itself. If we, during the webinar, I'm going to just have the everyone muted just so that we don't have a lot of extra feedback and whatnot. But I do want to mention that we have the chat and the Q&A boxes are available for you to submit questions or any chat comments at any time during the webinar. That would be great. Feel free to do that. And then at the end, as we have time, we'll go through as many of those questions as we can. So as questions come up, please just feel free to submit those. Yeah, that will be generally at the end. So at this time, I'm just going to go through a quick outline of what we're going to cover today, and then I'll hand it over to Kyle. So to begin with, Kyle's going to give us an introduction on high-speed imaging. What are some of the important aspects that we need to think about? How is the technology changing? How are we controlling high-speed cameras, and what are the relevant parameters to think about there? And then after that, Wing will be discussing specifically particle image velocimetry, or PIV. So he'll give us a description of the technique, the principle, how that works, talking about the processing, vector processing, and then branching out a bit and going into some of the more advanced PIV techniques, such as stereo PIV and volumetric PIV, some of the basics of how those are operated, and then going through a few application examples as well. So at this time, I would like to go ahead and hand it over to Kyle.
Thanks, Dan. So the question is, why do you need high-speed imaging for applications like PIV? The reason is because standard cameras nowadays are capable of recording around 300 frames per second, which is a frame, captured every about 3.3 milliseconds. And it turns out that the interesting physics that scientists and engineers are going for are, events on the time scale of 1 millisecond to 1 microsecond. And this kind of physics demands high-speed cameras that can record anywhere from 1,000 to 1,000,000 frames per second. All right. And with such high framing rates, and for example, if you record at a really high frame rate for, let's say, 1 second, you're going to need quite a bit of space to capture all that data. So these cameras not only come with high frame rates, but also a large memory storage to capture. So it's not uncommon to have cameras on the order of 288 gigabytes worth of storage, RAM storage. Something that has changed in recent years, there has been a push not only to get high, but also to couple that high frame rate with high spatial resolution. And if you look on the right there, typically the trend is, for the most part, high-speed cameras are on the 1 megapixel realm. And then there are some cameras that go all the way up to 9 megapixels. And usually as you go up in your resolution, you go down in your frame rate. So typically what you have to do is, based on your experimental parameters, you have to pick what spatial resolution and temporal resolution will fit your application. So I just wanted to take a step back and talk about the basic camera architecture of most high-speed cameras. Okay, so typically it's like a standard camera here. You have your lens, all right, and this comes in a variety of different models, types. It connects to a lens mount, okay, and right behind that lens mount is arguably the most important part of the camera. It's the CMOS sensor that is responsible of converting the light into digital data. So it basically is responsible for creating your data for your image, and all that data is written quickly to a RAM buffer. That is the only type of memory storage that is capable of taking such high throughputs of a high-speed camera. So that RAM buffer, you can store that data and it can be moved to a removable hard disk, or it could be sent off the back of the camera via Ethernet. And on the back of the camera, there's also, we can power it with wall power. You can put a backup power in there. You have all sorts of different camera signals coming out of the back. For example, something I'm going to talk about in the coming slides, something called your strobe signal, your F-sync signal, and so forth. And also you can add a hardware trigger to the back of your camera as well. And if you wanted to command some of these cameras without a laptop, we also have onboard camera controls that allow you to basically operate the camera using a little monitor on the camera if you wanted to do that. Really the workhorse of the whole system is the CMOS sensor. So what is that? What a CMOS sensor is, it's basically an array of pixels that span the X and Y direction. All right, this technology was invented in the 1960s. It was modernized in the 1980s. And basically every imaging technology that you have around you today it probably has a CMOS sensor in it, anywhere from your cell phone to your computer. And any other type of handheld electronic device that has an image capability, and the reason for that is because just the architecture is overcoming something what some people know of as the CCD sensor, which I'll talk about in the next slide. And these sensors come in a couple varieties. You can either get a color sensor or a monochrome sensor. For the most part, scientists that don't need any color information for quantitative means, they go with a monochrome sensor because it is more sensitive. It can see into the near IR, which color cameras cannot. They are blind to the near IR. And you don't get certain types of edge artifacts with monochrome sensors as you would with a color sensor, okay? And these CMOS sensors, again, are capable of anywhere from 1,000 to 1,000,000 frames per second. And they're capable of exposure times on the order of 250 nanoseconds and less, okay? And just a little bit of information about the CMOS sensor and how the color works is what we do and what most people do is they put on top of the sensor a Bayer pattern, okay? And the Bayer pattern is essentially R, G, and B color filters that are placed on the surface of the monochrome sensor. And basically the red filter will allow red photons and reject all the other ones. The green will allow green and reject the other colors, and so on and so forth, right? So that is used to generate an RGB image. If you look at the electron image on the bottom, that is basically a slice of a CMOS sensor. So a lot of the CMOS sensors have what are called micro lenses, okay? These micro lenses help to direct light into the sensor to basically increase the number of photons hitting that sensitive PN junction of your silicon sensor. So the micro lens focuses light through a color filter and into that active area where essentially photons excite electrons to create an electrical charge, which gives you your image data. Okay. And I just want to show you how it works, how basically images are created and how they're sent off the sensor. When growing up, this CCD was something that you would hear often, and that stands for charge coupled device. So this is an image of a pixel array that's being excited with a flashlight. So once you shine light on that pixel array, you have charge generation, right? Every pixel starts to basically get some charge. And the way that data is read off is through something called a shift register, okay? So that data is shipped off the sensor and it basically goes to a separate hardware where you have analog to digital conversion and you have amplification and so forth, okay? So the newer technology is your CMOS sensor, which stands for complementary metal oxide semiconductor sensor, okay? And I drew it a little bit differently here because a CMOS sensor actually has the amplifier and ADDs integrated into the sensor itself. So when you shine light on it, you have the same type of behavior, okay? You have charge generation. But the key difference is instead of the data shifting off the sensor, the data can be pulled off in a rapidly parallel fashion, which allows you to get the higher frame rates and the higher speeds, okay? So we take these sensors and we take these cameras and we can pair them together for applications like for any type of stereo application. PIV is, stereo PIV is the example here. So for example, the way we do it is, for example, if you have two cameras and you want to know, quantitative information about a volume or an event that's happening in a volume, right? What we do is we take a master camera, okay, which has a crystal oscillator that generates, you can think of it like a sinusoidal wave, okay? And that we have a second camera that also has a crystal oscillator in it, which also has an oscillating wave in it, which controls how the camera is capturing frames and also the rate, okay? So what we do to synchronize them is we take that master camera's signal, right, its oscillating signal, and we feed it into the slave camera through something what is called the F-sync signal. And that slave camera will essentially be in phase with the master camera, which allows you to get, on the order of nanoseconds synchronization with the master camera. So you're essentially taking pictures at exactly the same time, okay? And the last thing I want to mention before we progress here is it's really important that when you connect these two cameras together, that your trigger mechanism is also parallel, okay? So think of it, for example, here's a pickle switch drawn. This pickle switch essentially has a parallel split that goes into both the master and the slave cameras so that when you press the trigger button, each camera gets a simultaneous trigger and the cameras not only will be in sync, but it'll also trigger at the same time, which is in contrast to if you were to press a software button on your control laptop, because the software button, it operates via Ethernet, okay? And Ethernet is a serial way of communicating to the cameras. So that ultimately will give you a difference in when the cameras are triggered, all right? So the two key takeaways here are we can synchronize these cameras using the F-sync signal, and we can trigger them at the same exact time using a pickle switch in parallel, all right?
Okay, great. Kyle, thank you very much. That's very, very helpful and a good introduction for the high-speed imaging that will be used for PIV. So at this time, I'd like to hand things over to Wing, who's going to be talking about particle image velocimetry and its variants using high-speed cameras. Wing?
Okay, well, thanks, Dan. Thanks for the introduction. So let's take a look at this flow measurement techniques, particle image velocimetry, or PIV. This techniques has been used for flow research for a number of years, actually more than 3 years. Imaging techniques, that means that what you can see from the flow field that essentially can be measured. So one thing I like to mention before I go on to describe the technique is that since this is imaging technique, so it does require some kind of so-called seed particle to be introduced to the flow field. So the seed particle has to be having the same density as the fluid so that it can really represent the flow field correctly. So that is a different topic that we can talk about. But again, the seed particles are needed to be introduced to the flow field so that we can really follow the flow. So take example of the image over here. So you can see actually the different particles movement from the top and the bottom. And then in the middle of the flow field, you can see actually pretty complicated flow arrangements. But the image here is showing the particle movement. Another example over here is a water jet, a jet of water droplets. So again, like what we are seeing essentially is the movement of the particle within the flow field, representing really what's going on with the flow. So if we zoom in a little bit more, in fact, we can actually see the individual particles representing the fluid, the flow field. So going back to the PIV, so essentially PIV is a quantitative technique to show you what you can see. And then because you can see the entire flow regions, the measurements are actually taking place in many points at one instance of time. So if we apply the PIV techniques and then take many images, you can actually get some kind of statistics. For example, is the average velocity field or some kind of turbulence intensity measurements based on the number of captures that you do with the flow field. So one of the examples shown over here is that this is a velocity field of a vortex shedding behind a cylinder. So what you can see is the velocity vector fields showing the positive and also the negative vortex generated from the cylinder. So at the end, when you apply the PIV techniques based on the flow field, you actually can get a velocity field from the techniques as a result. So let's take a closer look of what really constitute a PIV system. So as I mentioned a bit earlier, seed particles have to be added into the flow field to represent the fluid motions. So the first thing is to have a particle laden field, but we need to have some kind of illuminations to be able to see the particles. So generally, we use a laser light in order to have sufficient amount of energy to illuminate the tiny particles that represents the flow field. Depending on how we're going to be generating the light, so it can be a sheet of light or it can be a volumetric sheet, a volumetric of light. So again, we are going to go into that a little bit later. So effectively, we are going to be taking two images with a short time between the two captures. And then these two images are compared to determine the particle displacement, or essentially how much movement of the particles represent the flow field. And then based on the particle displacements, knowing the time between these two images, then we can calculate the instantaneous velocity field. So I just want to show you a kind of typical system showing over here. So this is a system using of a mass flow field around mass, N95 mass. And then as I mentioned a bit earlier, we need to provide the seed particles into the flow field. So this is a generator, a particle generator to introduce about 1 micron particles into the flow field here. And then there's a lasers to illuminate the particles. This particular case is a sheet of light to illuminate the particles. And you can see the camera here doing the image captures to take these two separate images, separate by the time between the two images. And then the image information is fed into a computer software to do the analysis to give us the velocity field. Okay. So again, like the laser is generating a light illumination, and then the camera is taking the two images. Then there's a synchronization unit, essentially is the one that set up the time between the laser illumination and also the camera image captures. And then the software is to do the acquisitions plus the analysis of the image to give you the velocity field. So let's take a look of like how exactly PIV works. What is the principle behind PIV? I mentioned a bit earlier, so the laser is to use to generate sufficient amount of illuminations to see the small particles representing the full field. So as you can see from these schematic diagrams, the single light is spread out into a sheet of light using some kind of cylindrical lenses. And then this sheet of light is to illuminate the particles representing the flow fields. So the cameras here located around here is to capture two separate images. So one image at instant time of equal to t and separated by a small delta t. So the second image is going to be t plus delta t. So we know exactly what is the time difference between these two separate images. And based on the correlation techniques, which I'm going to talk about a little bit later, we can find out the displacements of this group of particles between these two particular frames, as shown over here. So once we know the displacements of this group of particles by dividing by the delta t, then we'll be able to get actually the velocity vector field. So the subsequent result, if we do that repeatedly in the entire regions of the flow field, what we can get is a velocity field represented over here. So this is a very typical image captured by the PIV techniques. As you can see, the raw image of the particle movement. So for this particular case, you can see image A and also image B, and also the movement of the particle from image A to image B. And if you look carefully enough, then you can probably see the movement of particle going from the bottom to the top, so in upward direction. So now let's take a closer look of the techniques to give us the velocity displacement. So the techniques that we've been using is called the cross correlation technique. So since you remember the image from the previous slides, all the particles look almost similar. It's really difficult to be able to identify individual particles to get so-called the individual particle displacement. So the cross correlation technique is a statistic approach to find the most likely displacements of a group of particles. So in fact, like instead of looking at the individual particles, the image captures as frame A and frame B, they are actually broken up into small regions called interrogation regions, as shown over here, spot A and also spot B. Okay, so when the cross correlation techniques is applied to spot A and spot B, we are able to actually get a displacement based on the movement of the particle from A to B. So it is shown over here. This is the cross correlations results showing a peak representing the displacements of that particular group of particles. So once we know the displacements of that particular group of particles, since we know the delta t, the time between the two frames, frame A and frame B, then we are able to actually calculate the velocity vectors representing the spot A and B. So essentially, again, like knowing the displacements based on the cross correlation techniques, which represent the most likely displacement of that group of particles, and divided by delta t, then we get a representative velocity vectors. So if we repeat the entire the process for the entire image of frame A and frame B, so essentially, again, you look at individual integrating regions, then we be able to actually get the individual velocity vectors representing each individual's interior regions. So by doing that multiple times, then we are able to actually get the velocity vector fields. So again, this is a result based on the cross correlation techniques to get like the flow field of flow behind cylinders. Again, it shows the different type of vorticities generated by the cylinders, like is a negative negative flow, counterclockwise flow, and also positive clockwise flow generated by the cylinders. So this is a picture of the vector based on the cross correlation technique we just look at. So again, like by looking at the movement of the particle, we know that the flow is moving from the bottom to the top. So this is actually a jet flow coming from the bottom to the top, and actually the cross correlation techniques can really resolve very small, tiny motions, as you can see over here. There's a recirculation shown over here with a very tiny velocity displacement or particle displacement, same as over this side. So there is a different circulations on this side, and again, it can resolve very tiny particle motions to give you the velocity vector field. So we've talked about the principle of PIV and the techniques to get the velocity vector fields. Let's take a look of the different types of PIV systems. As I mentioned, the system requires some kind of imaging. These are imaging techniques that require how the illuminations is going to be provided to the systems. So depending on the laser light illuminations, we can have the laser light in a sheet, in a plane, so that in that case, we get the planar PIV type of arrangement. Or if we have the lasers to be in a volumetric illuminations, in that case, we'll be able to illuminate the entire volume to get all the velocity component from that volume. So let's take a closer look of the different types of the planar PIV and also the volumetric PIV. So for planar PIV, essentially there are two types of planar PIV systems. So one is using a single cameras, meaning that we are getting only two components from that plane of laser light or two-dimensional. We can also get the third component, essentially the component going in and out of the laser light sheet by adding another cameras. So in that case, we are able to get the three components of the velocity, again, on the same planar illuminations. So both the 2C or 2D or 3C, 2D, the planar measurement essentially gives a slide of the flows, providing really a projection of the flows onto that particular slide. So as you can see, it's actually very important to know the orientation of the slide, because essentially the orientation of the slide represents the projection of the flow onto that particular slide. So it can give us some understanding of what's going on, but essentially it's really only a partial understanding of the flow based on the orientation of that laser light sheet. On the other hand, as you know, flow is always like, most of them is like volumetric in nature. So it's very beneficial to be able to actually look at the entire flow field in a volumes. So in this particular case, we are able to actually get all the components, meaning the U, V, and W in that particular volumes. The requirement for that is to add additional cameras. I mean, for planar PIV, we can use a single cameras or two cameras for stereoscopic PIV, but for volumetric PIV, it's required to add another cameras or even two cameras to be able to view the volume so that the particles within the volume can be identified properly. So the benefit of that is that we can get a complete quantitative understanding of the flow structures in that particular volumes. So if we use the high-speed cameras, what I talked about earlier, then we actually be able to get the so-called fourth dimension as well, meaning that we are able to really track what's going on of the flow field with respect to time. So we can find out the evolutions informations of the unsteady flows. So I want to show you an example of the different type of informations provided by a planar and a volumetric PIV systems. So this particular study was done at Harvard University, and it was a study of the flow behind a shark tail wake. Essentially, it's the wake flow generated by the shark tails. The flow is very unsteady because of the movement of the shark. So the planar PIV and also volumetric PIV was taken for this particular study. So if you look at the picture over here, so this is a result from planar PIV image captures. So what we see here is really the vortex generated by the tail, the wake flow from the shark tails. So you can see from this result that, okay, we can identify some counterclockwise vortex and also some clockwise vortex in these two particular pictures. The information obviously is very useful because we can see the different location of the vortex generated by the tail, but it's still limited to a planar information. So if volumetric PIV systems was used to do the measurements, and all of a sudden you can see not only the vortex locations, but really what is really happening surrounding the vortex locations. So using the volumetric PIV measurements arrangement, we can actually see the entire actually vortex ring generated by the tail of the shark. And in addition to just the volumetric informations, again, we use high-speed cameras. So in this particular case, not only that we can see the evolution, I mean the volumetric structure of the vortex generated by the shark, but we can also see how the flow is evolving with respect to the movement of the shark. So again, in this particular column, you can see the time going on from time equal to 0 to time to 0.066 seconds, and the evolution of the vortex string generated by the shark in three-dimensional fact. Likewise, using the 2D systems, we can also see some information, the evolution of it, but again, not as good as having the entire structure to be explored using the volumetric PIV systems. So let's take a quick look of the typical type of system arrangements for a 2C, 2D PIV systems. So again, like we mentioned a bit earlier, it requires imaging systems. The imaging system typically is the lasers. The reason why we want to have lasers is to have sufficient amount of energy to be able to illuminate those seed particles. Again, the seed particles typically are very small in size, maybe like 1 micron to up to 10 micron in size. So sufficient amount of energy is typically required in order to illuminate those tiny seed particles. Occasionally, we also need to have some kind of beam delivery systems and then the light shield optics. And the picture over here is a high-speed lasers. It's very big in size, so that like a beam delivery system can be very helpful to allow the laser beam to be delivered to where your research is taking place or your model is located. So again, the light optics is to illuminate a single beam coming out, as illustrated from these pictures, to generate a laser light sheet, or depending on whether it's going to be a volumetric systems, to also generate a volume of light. Okay. The lasers also is very useful because the pulse energy is very high, and also the durations for each laser pulse is very short. That means that we can effectively freeze the motion of the particles to truly represent what's really going on of that particular instant of time. And then for time resolved system using high-speed cameras, this kind of lasers, high-speed lasers, can also be pulsed really quickly in conjunction with the cameras. So we are able to get the time resolved information at like 10,000 frames per second or even higher than that. And as far as the image captures, we talk about using high-speed cameras. So this is one of the example of the high-speed cameras. So the high-speed cameras is usually synchronized with some kind of timing electronics to make sure the image captures coincides with the laser pulses coming out from the lasers. Okay. So essentially, the high-speed camera is to use to capture the image particle images and record them, put it into the RAM as as I'll talk about a bit earlier. And then once the data is captured in the cameras, the data is going to be transferred to the computer, and the computer essentially does the data acquisitions, and then using cross correlation techniques to analyze the image to give you a velocity vector field as shown over here. Again, this is a vector field of the flow behind a cylinder showing the positive and also negative circulation motions. So this is a very typical system arrangement for 2C, 2D. And just keep in mind that like when we go into the stereoscopic system or volumetric systems, many of the same components are going to be used. So essentially, we will use similar lasers, similar laser optics. The additional thing is really the additional cameras that we need to add to the system in order to get to, let's say, the stereo and also the volumetric PIV system. So we like to show an example of the imagings of a person coughing. So Kyle, you want to describe that a little bit better?
Yeah, this is an example that we did. It was taken with our most recent camera, the Phantom V2640, a camera that can do 6,600 frames per second at 4 megapixel resolution. And this is an example of some research being done to better understand how droplets and aerosols basically emerge when a person coughs. And basically, Vision Research and TSI work together to take this data and to analyze it to get quantitative data from this information.
Okay, so let's take a look of the results. Generated by the previous image. So using the cross correlation techniques, we are able to actually get the velocity vector fields based on the droplet motions that you see on the previous slide. So again, you can see the power of the cross correlation techniques based on that we'll be able to get the quantitative result showing the vector fields of the same image captured a little bit earlier. Okay, so let's take a look of one of the examples of a 2C, 2D systems. So this is an example that we talked a little bit earlier. So for this particular case, the investigation was to look at the flow around a N95 mass. So again, like we mentioned earlier, we need to provide the seed particles to represent the flow field. So there is this seed particle generator over here to show you to fit into the flow field areas to represent the flow fields. And the lasers are located over here to generate the laser light sheet. And this is the model that we are looking at the flow around this particular model with the mannequins, without and with the mask on that. So the high-speed cameras is located 90 degrees with respect to the laser light sheet to capture the images. And then the image is fed into the computers for us to do the analysis. So to give you a little bit more details, the Phantom VO440 cameras is used for this particular case because we want to really be able to capture a high-speed image from the flow field. And then the laser is continuous wavelength lasers and then there's a laser light sheet to generate from the single beam onto a laser light sheet. The electronics is kind of behind that. This is again to make sure that synchronization of the cameras captures and also the laser light are going at the same time. So again, the seed particle is generated from this NASCAR nozzles, and the software inside 4G was used to do the image captures and also the analysis. So you can see the image over here that shows the velocity magnitudes in the 2D arrangements, meaning that we can get U and V component of the velocities. So for this particular case, it appears that like there is a kind of motion going, the air motion actually going into the mass through around the nose area. So this is a very good technique to find out whether there's any leakage through the mass. And then it showed that like there could be some leakage around this particular area. And again, the different color represents a different velocity magnitudes. So this area is showing that there's a lot of air actually getting inside into the mast. So again, the high-speed cameras allow us to do this kind of investigations to find out exactly how the flows behaves, and also how you can change with respect to time. So we talk about a planar PIV getting the U and V component. Well, let's take a look of the third component, because there could be a lot of interest to find out exactly whether there is any float coming in and out of the laser light sheet. So let's take a look of the planar stereo systems. We call it 3C, 3-component, 2-dimensional. So if we use an additional cameras and arrange the cameras from 2 perspectives, we are able to actually get the motion in and out of the laser light sheet. So effectively, we'll be able to extract the 2, 3-component of the velocities based on the 2-component vector fields captured by the 2 cameras. The techniques that require calibrations or mapping functions, we're not going to go into that, but it requires a calibration to allow us to understand exactly what the behavior of the path of motion captured by the 2 cameras. So in this case, the result is that we'll be able to get the U, V, and W component from this particular 2D plane. So let's take a closer look of the stereo PIV arrangements. So the schematic diagrams over here shows the arrangement of the 2 cameras with respect to the laser light sheet. Again, this is the laser here. It generated a laser light sheet. So we'll be looking at the top of the laser light sheet. So the interest here is look at the particle movement getting in and out of the laser light sheet. By having the 2 cameras arranged in such a way, as you can see, each camera look at a projection of that particular vector field and project it onto the cameras. So you can see over here, this particular cameras look at the projection over here, which shows a longer 2D vectors. And then this particular cameras is showing a shorter version of the projections because of the angle is back to that particular vector field. Another thing I want to mention is that there is a so-called sign flow arrangement. This is arrangement to allow the cameras to be able to focus onto the light sheet perfectly, because as you can see, the camera is looking at the light sheet at some angle. So naturally, there will be some kind of perspective distortions. But having a sign flow arrangement, we can remove the perspective distortions and making sure that all the particles illuminated by this light sheet are perfectly focused onto each camera. So this is a very necessary arrangement for a stereoscopic PIV. So again, essentially, we are using 2 cameras to view the 2 perspective of the flow fields. And the result is to look at the particle movement, not only onto the plane, but also the in and out of the plane. One requirement for that is that we need to have some kind of calibrations in order to register these 2 cameras with respect to the laser light sheet. So essentially, we are going to be establish some kind of relationship between the camera's image and also the image of the laser light sheet, illuminated by laser light sheets. By having these 2 pieces of information, we combine the informations to actually calculate the velocity vectors in the W direction, which is in and out of the laser light sheet. So let's take a look of the typical system arrangement for a stereoscopic 3C 2D systems. So again, like the PIV lasers and laser light sheet optics, which is really the same as the 2C 2D arrangements. In addition to 1 cameras, we also need to add another cameras, as you can see from the previous slide. Another thing that I mentioned a little bit earlier is also the sign flow adapters. So we need to have the sign flow adapters to be used for each cameras, so that each cameras can be focusing on the laser light sheets perfectly without any effect from the perspective distortion of the cameras. In order to do the calibrations, we need to have a calibration target. Essentially is to establish the relationship of the particle image from a target to the particle image on the cameras so that we know what the distortions is going to be affecting the particle displacements. So the synchronization unit is the one that we also use for a 2C, 2D systems, and then the software to analyze, to take the images and also to analyze the image to give the third component of the velocity a particular plane. So with information, let's take a look of one applications of a turbulent boundary layer flows. This particular study was done actually at University of Illinois, Department of Mechanical Engineers. I want to go over this particular experiments quite in details. As you can see from these pictures, again, like since it's a stereo systems, so we have actually two cameras looking at the flow fields. And I mentioned about the calibration. You can see the calibration target over here. So these two cameras are arranged such a way that both of them are looking at this calibration target. And it's a little bit hard to see this particular modules, our piece over here is the sine flow mount, meaning that it allows us to change the camera respect to the camera lens so that the cameras can be focusing perfectly onto this particular target. So this picture really shows the calibration process that we need to do in order to establish the mapping functions to get the correct velocity vector field result. Okay. So this particular study is a turbulent boundary layer, meaning that actually at the bottom of this water tunnel is a wavy surface. But it's difficult to see. The reason is that because this is a so-called refractive index matching tunnel. It means that the model that makes up the wavy surface at the bottom here is actually matched with the fluid having the same refractive index, meaning that like the fluid inside the tunnel has the same refractive index as the model. So the consequence is that although there's a model here, but it's really difficult to see because the refractive index of the model and also the fluids is exactly the same. So that's the reason why you cannot really see the model so clearly over here. And the question is, why do we want to do that? The reason is that if the model can be seen, then there will be some kind of obstructions of the model to the flow field captured by the camera. So having the refractive index matching tunnel, meaning that index of reflection of the model and the fluid is the same, then essentially there will be no obstructions due to the model itself. So that would really help for the cameras to look into even a tiny region of the model to really extract the information from the model. So again, going into a little bit more details, the lasers is a high-speed laser with 20 millijoules per laser pulse. The two cameras are the lab 340 4 million pixel cameras, again in this stereo configurations. The stereo sound mount are used for the cameras as shown over here, and also shown over here. This is a stereo sound mount, the timing electronics, and also the inside 4G software package. So again, this particular picture shows the sheet of light generated from the lasers in the bottom over here. So you can see the lasers generate the laser beams and then convert into a sheet of light illuminating this index matching tunnel. So again, these two cameras on each side of the tunnel to capture the movement of the particles. So with this, let's take a look at the result. Okay, so this is the result generated by the stereoscopic systems in this picture that you saw in the previous slides. So first of all, let's take a look at the velocity profiles. Again, like since it's an index matching tunnel, so we are able to see through the model because there's really no obstructions of the model itself. So this is a profile of the flow field showing across the width of the tunnel, okay, in the cross-section directions. And these two particular columns, the picture over here is the turbulent kinetic energies at different flow rate. So the picture over on the left-hand side is that low Reynolds numbers, lower flow rate. And the picture on the right-hand side is higher Reynolds number, meaning that at a higher flow rate. And it's also a comparison between a planar 2C 2D versus a planar 3C 2D. So you can see over here that this turbulent kinetic energy is only taken by a single camera representing 2D information at the no Reynolds numbers. So the information of this turbulent kinetic energy shows some high turbulent kinetic energy on the trough of the turbulent boundary layer. But by doing the 3 components of the measurements, actually we miss a lot of third component coming into the flow field. So you can see kind of drastically different information if we actually use the 3C information of the measurement. So similar phenomena we saw from a higher flow rate and a higher Reynolds numbers. Again, based on just the 2D informations, the limited information of the turbulent kinetic energy that we saw, particularly on the trough area of the turbulent bound layer. But by using the stereoscopic systems, we were able to actually see much more details, meaning that there's a strong third component going through the light sheet, generating a much higher turbulent kinetic energy that we can discover using the stereoscopic arrangement. So you can see the benefit of the stereoscopic arrangement compared with just a planar 2C, 2D arrangement. Because particularly for case with strong third component across the laser light sheet, there's a lot of useful information that can generate from the stereoscopic PIV system. So now we talk about the planar PIV systems, 2C, 2D or 3C, 2Ds, and those are very useful information that you can get. But naturally, flows are very three-dimensional in nature for most of the time. So it's very beneficial to be able to actually use a volumetric 3C, 3D systems to investigate the actual flow phenomena in a volume. So I want to show you pictures of a volumetric PIV systems. So again, I will go into a little bit more details. So typically, the system components are pretty similar to the system component that we talk about on a planar PIV. We use the lasers to illuminate the flow field. We use cameras to look at the flow field, synchronization unit to synchronize the timing of the image capture and also the illumination of the laser light and the sign flow adapters. But for volumetric systems, we need to have at least like 3 or 4 cameras in order to be able to look at the particle image and identify the particle image in the flow field correctly. So in addition to the laser light illuminations, we typically use, again, 3 or 4 cameras and the camera lenses. And like we mentioned earlier, the sign flow adapters is important to allow the cameras to be focusing on to the volumes correctly, making sure that they are looking at the particles with focus images. Because again, the cameras are arranged in such a way that they have some kind of perspective distortions to the flow field. Again, the synchronizers is used to synchronize the image capture of all these 4 cameras and with the laser light pulses and to capture it correctly. And for this particular case, the different piece of software for us is the Insight V3 software. It's going to be used to do the acquisitions and also the analysis. One of the arrangements for the volumetric PIV is to actually have the cameras in different configurations. So one of the common arrangement is to have a so-called single line cameras arrangements, like what we show in this picture here. So you can see that all 4 cameras are put onto a single line arrangement. What is the reason of doing that? The reason is that having all cameras in a single line arrangement is actually quite robust and easy to set up. In this kind of arrangement can also be used in airflow and also water flow. So for this particular case, water flow applications. And the nice thing about having a single line arrangement is that you can see from these pictures, the perspective distortion is only in one direction, because again, the camera is looking at this particular flow field on this plane, so the perspective distortion is only in one direction. So all we need to do is to use a sample amount to make the correction of the perspective correction, like what we do with the stereo PIV arrangement. Occasionally, we can also make this arrangement easier in a sense that we can also make that to be in forward scatter direction with respect to the laser light sheet. So that could be a lot of benefit having the camera in the forward scatter direction, meaning that we can actually get more light from the particle illumination. So with this information, let's take a look of the operation principle behind volumetric PIV systems. So the process is actually quite similar as the PIV system we talked about a little bit earlier. Okay? So there is a camera setup and a calibration process is required to do that so that we can actually relate the particle image captured by the cameras to the particle movement in the flow field. So then we do a calibration process to establish that particular relationship, and then we do the image captures, and then there is some kind of pre-processing to get the particles to be recognized, and then the analysis to get the velocity vector fields. So let's take a closer look of all the different process for the volumetric PIVs. And again, like the camera setup, these are flexible camera arrangements. So for this particular case, we see 4 cameras arranged in a rectangular format. So the cameras at the corner of a rectangular arrangement. So the cameras are looking at the lasers. This laser illumination is no longer a sheet, but actually a volumetric illuminations. So you illuminate the entire volume where the measurement is going to be taking place. So we use a calibration target, essentially target long dot spacings, to establish a relationship between the image captured by the cameras and the actual location of the particle in the volume. So effectively, we can see what's really going on between the particles and the actual volumes in the fluid space. So once that is established, then we can go ahead actually doing the image captures. So the image capture is actually very similar to the PIV. Like we mentioned, we take 2 set of images separated by a delta t. Knowing the delta t, then we'll be able to actually track the particle movements and get the velocity vectors. So since we're using 4 particular cameras, so you can see that there are actually 4 sets of 2 images. So frame A and frame B, as we illustrated a little bit earlier in the previous slides. So once the images are captured by the 4 cameras, then we go into doing the analysis of the particles. So the first step is we look at the individual particle captured by the cameras. So it is to identify the particle for each cameras. Again, based on the information for the 4 cameras, then we actually use the triangulation techniques to get the particles of these 4 cameras to map it back into the fluid space. So this 3D particle matching is to use triangulation techniques to get the 2D particle images from the 4 cameras and put it back into the volume. So as a result, then we actually can get some kind of particle image in the volumes. And again, instant of time, so-called frame A and also frame B. So after the particle matching, then we get 2 particle clouds at 2 different instances of time. And then the techniques to get the velocity vector is not the correlation technique typically used in planar PIV. We actually use a particle tracking techniques. And the reason is that it would give us the best spatial solutions, because effectively we are tracking individual particle movement within the volume. So ideally we are able to track individual particle to get one velocity vector from each particle pair. So again, like we know the time between these 2 volumes of particles, and knowing the displacements by tracking the movement of the particles divided by the time that we get the individual velocity field from the volume. So the individual velocity field in the volume is very useful, but if we need to get some kind of statistics or vorticities, generally we need to have that information in a gridded format. So we typically do a velocity interpolations in order to get the velocity field in a gridded format. Subsequently, we'll be able to get, let's say, the vorticity informations or turbulent intensity informations. So this is a result, again, of a water shedding of the cylinders. So if you remember that using the planar PIV systems, we are able to see some information of the water shedding, but using the volumetric system, we actually can see the entire vorticity field generated by these particular cylinders. So the information is much more complete. And again, using the high-speed system, we are able to see essentially the change of the flow with respect to time as well. So with this, let's take a look of a couple examples of the volumetric PIV systems. So the first example is a wind tunnel flow measurements, and the measurement was conducted at the Aerospace Department of the University of Minnesota. So you can see the picture over here. This is a wind tunnel, is about 1 meter by 1 meter in size in the test session area. And then there are 4 cameras arranged in such a way that is on a rectangular arrangement, meaning that each camera is in the corner of the rectangular shape. Okay, so all the cameras are focused onto volume illuminations. You can see over here, the laser is from the bottom of the tunnel to give us a volumetric illuminations. Okay, the sample mount was used so that the cameras can all be focused onto the volume, seeing the particles, focusing with the focus perfectly. So we'll go into more details. The 4 cameras are VEO 340 4 million pixel cameras in the volumetric PIV arrangement. And then the lasers was a high-speed 30 millijoule lasers. Again, the laser was in the bottom of the, I'm sorry, the laser sector on top of the tunnel. You can see the laser beam coming over here. There's a mirror to direct the beams into the test sessions. And the light here is the volumetric illuminations. The acquisition was captured about 800 captures per second, meaning that the camera frame rate was 1600 frames per second. The purpose for this particular case is to characterize the tunnel flow profile. So effectively, there's no no object inside, so we want to find out what is the flow behavior with really no objects in the tunnel. So let's take a look of the result. So again, since the purpose is to characterize the flow inside the tunnel with no object inside, so effectively what we want to see is really uniform flow arrangements on the entire test sessions. So you can see over here that like the typical velocity flow field is around maybe about 2 meters per second, 2.5 meters per second, except there's some, I would say, disturbance of the bottom of the volume. So the flows appear to be very uniform across the entire volume measured by the systems. So again, for this particular case, the volume size was about a 13 by 7.5 by 5 centimeters. Again, the camera lens was used is the 50 millimeter camera lens with the f number of 11. And the reason why we use that because we'll be able to focus the particles within the volumes perfectly using the camera lens aperture and also the cipher arrangement. Okay, so let's take a look at another examples. And this particular case or measurements is a flow around the Bakken Dune. So effectively, is looking at the wick flow behind a Bakken Dune. And the measurement was taking place at the Department of Mechanical Engineering, University of Notre Dame. So let me describe the system setup over here. So you can see the 4 cameras again arranged in a rectangular format, meaning that each camera is at the corner of the rectangular shape. Over here is the high-speed cameras. The laser is coming from the bottom of the tunnel to illuminate the volumes. The tunnel behind that is also index matching tunnels. Again, for the same reason like I described it earlier, the 4 models has the same refractive index as the fluid so that whatever we want to see, we can see through without any obstructions by the full model itself. So we can see from the result a little bit later on. So this is a refractive index tunnel. So although the full models is inside, it's really difficult to see because again, they have the same refractive index. So from a naked eye or from the cameras, the cameras cannot really see the model at all. So to give you more details, the VEO 640 cameras, 4 million pixels are used. As you can see from this picture over here. The high-speed laser is from Northrop Grumman's high-speed laser is 30 millijoule per pulse. Again, like since we look at the very tiny particles, the energy is required in order to illuminate those particles. Synchronization units is used to synchronize the image capture and also the laser pulses. And then the software, the Inside With 4G software was used to do the image captures and also to do the analysis to give us the velocity vector fields. So let's take a look of the result from the measurement. So the measurement is look at, again, the wake flow behind a Barken dune. So you can see the positive and also the negative circulations, essentially the vortex generated by the Barken dunes. This is a closer look. This is a closer look of the vortex shedding from the dune itself. So you can see the counterclockwise and also the streamwise vorticity directions from the results here. If you're interested, there are actually a paper generated from this particular measurement is a proceeding in the International Symposium of Applications of Laser Imaging Techniques to Fluid Mechanics. So with that, I'd like to conclude the discussions that we had. So we talk about the high-speed cameras, the design, and how high-speed cameras actually operate. We also have an introduction of the PIV systems, how the PIV systems can be benefited by using high-speed cameras. So having the time result measurements is actually very important to understand what the float field looks like and how it evolves with respect to time. And using the high-speed cameras, we are able to actually capture so-called high temporal resolution, meaning that we can track the fluid motion with respect to time. For volumetric PIV system, we are able to see the UVW component in the volumes. So again, we also talk about the different type of PIV systems, the planar and also volumetric PIV systems. And both planar and also volumetric PIV system offer the flow field informations to give you the understanding of the flow structure with different perspective. So planar, we can have the 2C2D or 3C2D, and the 3C2Ds can be also very useful, as you can see from one of the examples on the stereoscopic PIV arrangement. And obviously the volumetric PIV is the best arrangement because in that case, you can see all the three components of velocity in particular volumes. Again, using the high-speed systems, we're able to also get the so-called fourth component, the time resolutions of the flow field as well. With that, I think this is the end of the presentations. So let me hand it to Dan to see what kind of questions that we can answer from the audience.
Sounds good. Thanks a lot, Wing. Thank you, Kyle. That was both very good presentations and very helpful, I think, for understanding the PIV and the use of high-speed cameras for PIV specifically. So we've got quite a few questions that came in, and what I'll like to do now is I'm just going to go through these and kind of direct questions to each of you depending on kind of the nature of the question. So we'll just keep going through questions, and any attendees that would like to send questions now, please go ahead and do that. And we'll get to as many as we can before we run out of time here. So Wing, I think the first question relates to PIV specifically. Actually, there were a couple of questions on this topic. One was, when using PIV, is it better to have a pulsed laser light synchronized with the camera, or better a CW signal? And then later on, a similar question asked, CW versus pulsed laser for PIV, how does it influence the image being captured? And I'd just be curious, how do you answer those questions?
Yeah, actually it's a very good question. Ideally, like the pulse light is more desirable, and the reason is that I think we talked about it a bit earlier too. The pulse light can give us a very short laser pulse, so effective. Let's say in the order of maybe like 5 nanoseconds or a little bit higher, maybe like 100 nanoseconds. The benefit for that is that because there's such a small laser pulse, would really help us to so-called freeze the particle motions. Particularly for really high speed flow, meaning the flow is running at very high speed. So the ability to freeze the particle motions, in that case, the cross correlation technique can give us a better result in terms of getting the displacements to be calculated. And the CW lasers, as you can see from one of the applications, can also be used. But for CW lasers, typically the duration of the pulse, as you know, is continuous. So effectively, the way that we so-called stop the duration of the pulse is really by the camera frame rate. So depending on how fast the cameras can be captured, so the amount of exposure time for the cameras to the lasers, it really depends on it's really the exposure of the particle motions. So for high-speed flow, if the exposure time is long, that means that instead of seeing really an instant of the particle image, we might actually see a streak of the particle image, because for that particular time when the exposure is on, the particle continues to move. So the consequence is that when we do the cross correlations, there might be a little bit uncertainty of exactly where the peak of the displacements is supposed to be located. So that it might have some kind of effect to the accuracy of the measurement if the CW lasers is used particularly for really high speed flow.
Okay, that's interesting. Thank you, Wing. This next set of questions, I think, Kyle, might be more applicable for you. The first one is, you described the CMOS sensor and the difference between the CCD and the CMOS. And the question is, if you could give a one-sentence summary of advantages of CMOS sensor, what 2 to 3 points might you highlight? And then the second part of that question was, what is the future of high-speed cameras for PIV in general, but also more pixels? Is there a limit to how the manufacturing is going for either more pixels or more speed, or perhaps shutter time? So just curious what you would, how you'd answer those two questions.
Yeah, so I think that, when you talk about CMOS sensors and you talk about CCD, the big difference is speed. In that diagram, basically, you can see that CMOS sensors can read off in massively parallel fashion. So speed is a big one. And when CMOS sensors originally came out, the image quality compared to a CCD did not compare, just because you have additional hardware, you have a lot of extra noise. But it's getting to the point where it's the technology is maturing and the image quality is getting better and better. So the CMOS sensor is definitely gonna be the front runner from here forward, the way we see it. So as far as camera development is going, vision research is essentially pushing forward in both directions, both the high resolution and the high throughput moderate resolution, right? When I mean moderate resolution, I mean the 1 megapixel. So we're constantly working on faster cameras in that regime, and we're also constantly working on cameras that have a higher spatial resolution as well. So yeah, both directions, and and it is purely market dependent. So if we see a niche where there's a sensor to be developed for that scientific application, that's where we will be basically developing for. And then the next system was, I think that was it for the couple questions. Was there another one in there? What was the limit to what manufactured? That's a great question. That is purely an R&D type question, right? So the goal of the engineers are basically to basically pump out as much data off a sensor as possible, all while maintaining the best possible image quality that you can get at that given throughput. So, I wouldn't be surprised, with exposure times, we're on the order of hundreds of nanoseconds, and in the future, you shouldn't be surprised to have even better than that, right? So, it's constantly heading in that direction. So, the order of millions of frames per second and on the order of nanosecond exposure times. Yeah.
Okay. Thanks a lot. That's helpful. Wing, a quick question on, you mentioned Insight 4G processing software. Is that used for data acquisition and data processing, or just for data processing?
Yeah, actually, the software supports different type of hardware, the lasers and also the camera. So yeah, it is used for data acquisitions and also the analysis as well.
Okay, great. Another question about the Scheimpflug adapters. How are the Scheimpflug adapters set?
Okay, So usually the sunflower adapter is mounted between the camera body and also the camera lens. So it's in some of the pictures you can see there is a piece of hardware that goes between the camera body and the camera lens. So depending on the sunflower arrangement, so typically sometimes we actually move the camera lens with respect to the camera body, or to move the camera body with respect to the camera lens. So the sunflower arrangement is to allow the camera image through the camera lens to be able to see through the particle image. Let's say for planar PIV systems, all the particles in focus without really like losing any information.
Okay.
So there is a particular so-called sunflower arrangement, and again, like we can probably get into a little more detail later on, but like maybe we can provide the information to the individuals, people for details. But yeah, the arrangement, the sunflower arrangement is to just to make sure that the particles are in focus onto the camera sensors.
Okay. Okay. Perfect. No, that sounds good. That sounds helpful. Yeah, we'll go ahead and continue to answer questions here for a few more minutes. So if you have those, please feel free to send them. I think this question relates to capture rate and specifically for PIV. So Wing, the question is 800 captures per second. Does this mean the time between 2 frames is 1/800, or it's the time between 2 flow velocity realizations is 1/800? And then the second part of that question is, what is the shortest time interval possible with time resolved PIV?
Yeah, it's a very good question. Yeah, let's say the capture rate is like 800 capture per second, meaning that the camera is actually running at like 1600 frame per second. The time between the two frames, particularly when we use the pulse lasers, is not 1/116. 1600. The reason is because like we can control the pulse lasers to different location of the exposure time of the camera. In fact, when we use the so-called frame straddling arrangement to make sure that the time between the two laser pulses can be appropriate in such a way that like, well, we can actually look at even for higher speed flows. So as you can imagine, like if we just use the delta t, the time between the two pulses, based on just the frame of the cameras, it limits the amount of velocity measurement that we can take, right? Particularly if the flow is really high speed. So using this so-called frame straddling arrangement, so we'll be able to actually use the pulse lasers to make sure that the time between the two pulses is really, really short. Let's say in the order of like one microseconds or even less than that. And and then that's the reason why the pulse lasers is actually very useful, particularly for high-speed flow measurement.
Okay. Yeah, thank you for that. And there's a related question, so I'll ask that now. Is there a limit to the velocities at which the PIV system can track? And I think what you just answered is kind of related to that as well.
Hey,
yeah,
Dan.
I mean, yeah.
So, go ahead.
So again, like depending on the time between the two laser pulses, and like Kyle was mentioning, that like we can actually capture two images with about like 200 something nanoseconds between the two frames. So effectively, we can make measurements up to maybe like even 1,000 meters per second, of course, depending on the field of view of the image captures. So
Yeah.
Yeah, I was just going to add a point to that. That's a great question, and where you can find that in the camera specification is you look for that, as Wing mentioned, the straddle time, which is basically it's basically our f sync signal, which has a really short little readout time, and it's on the order of hundreds of nanoseconds, and then some cameras on the order of 1 millisecond, or I'm sorry, 1 microsecond, right?
Good point. Thanks for mentioning that, Kyle. Okay, another question relating to interrogation regions in PIV. how do you define the resolution of the interrogation region? And would using a too small resolution at a high velocity cause the interrogation region to skip the particles and cause false prediction of velocity of the particle?
Yeah,
So
it's a very good question.
Yeah.
Yeah, the size of the interrogation region is actually determined by the users. So depending on how you want to get the information. So let's say you want to really look at to get a very high spatial resolution, the large vector fields. So laterally, you may want to actually reduce the interrogation regions to a smaller size so that you can get actually a higher spatial resolution of the vector fields. But obviously, the question is that, like you just mentioned, whether from frame A to frame B, whether you be able to keep track of it. Well, the software actually has techniques to allow the movement of the second frames respect to the first one, so that the same particle can be tracked by moving really the location of the windows of the second frame. So in this case, again, like it's hard to get into the details, but the software does have the capability to move the second interrogation windows so that the same particles can be still tracked.
Okay, that's helpful. Well, we're kind of getting to the end of our time here, and so I apologize if we weren't able to get to your question specifically. If you were able to ask one, we will try to contact you individually for those. But for Kyle and Wing, I just want to mention that the chat and the Q&A are coming through. Thank you for the talk. Lots of thanks and well wishes. So I just want to mention that to both of you guys. But at this time, we will go ahead and end the webinar. But before we do that, I just want to mention that the slides and the webinar recording will be sent out to all of the participants. So that question came a couple times. Yes, the slides and recording will be available. So you can expect a follow-up email within sometime in the next week or so, once we get everything uploaded and formatted in a way that's easily downloaded. So everyone, I want to thank again for attending the webinar. I want to give my special thanks to Kyle for giving such great talks, and we'll talk to you all next time.
Thank you.
Thanks, Dan.
Thanks, Kyle. Thanks, Wing.